Welcome to Cross-Connection Control Awareness, Part B. Today, we're going to dive into the rationale behind cross-connection control. As plumbers, you work with both potable and non-potable piping systems every day. It's crucial to understand what a cross-connection is, recognize situations that could lead to one, and know the methods used to prevent contamination of our drinking water.
Let's start by looking at liabilities and responsibilities. Protecting the potable water system is a shared duty. In Canada, jurisdiction is split between federal and provincial governments. Provinces handle health and local matters, and municipalities can only enforce regulations if provincial statutes allow them to. If regulations exist, ignorance of the law is no excuse. If contamination occurs, liability can fall on property owners, plumbing contractors, consulting engineers, municipal inspectors, and water purveyors.
Each party has specific roles. The water purveyor ensures safe water up to the consumer's premises. The chief plumbing inspector checks plumbing systems for hazards. The health department ensures water remains potable from source to tap. The consumer must install and maintain backflow devices. Certified testers ensure devices work correctly, and manufacturers must meet approval standards. Why is this so important? History shows us the severe consequences of cross-connections. For example, an epidemic of amoebic dysentery caused 98 deaths due to defective plumbing. Other cases involve pressure drops in factories, defective valves on ships, and peak demands in schools causing back siphonage. These incidents highlight how easily contaminants can enter drinking water. Other bizarre cases include antifreeze pumped into city water mains, blue toilet cleaner siphoned into drinking water, and hydronic heating fluids forced back into potable systems. In one instance, a college football team contracted hepatitis when surface water was siphoned into a drinking fountain line. These stories prove that constant vigilance is necessary. To prevent these disasters, we have regulations. The National Plumbing Code of Canada states that potable water systems must be designed so non-potable substances cannot enter. Specific articles address back siphonage, back pressure, fire protection systems, and the separation of private and public water supplies. Premise or zone isolation is also required for high-hazard buildings.
Now let's look at how contamination occurs. The first method is back siphonage. This happens when the pressure in a potable water supply becomes negative, meaning it drops below atmospheric pressure. If a supply outlet is open, like a hose submerged in a plugged sink, contaminated water can be sucked back into the clean water supply.
The second method is backflow caused by back pressure. This is an unintended flow into the system from an outside force that has greater pressure than the potable water supply. This can happen through an open valve, a failed check valve, or a failed control device, forcing contaminated water into the clean lines. The third method is gravity contamination. This occurs when an opening in the potable water system is lower than a contaminating source. It can happen due to a mechanical failure, like a broken pipe, or during installation and repair work, allowing contaminants to simply flow in by gravity. To prevent these types of contamination, we use cross-connection control devices. The most common methods are air gaps, atmospheric vacuum breakers, and pressure vacuum breakers. An air gap is simply a physical space between the water outlet and the flood level rim of a fixture. Vacuum breakers admit air into the system to break a siphon. For more complex systems, we use mechanical assemblies. A double check valve assembly is used for minor to moderate hazards where backflow is aesthetically objectionable. For severe hazards where backflow could be toxic, a reduced pressure backflow preventer is required. This device has two check valves and a relief valve that dumps to the atmosphere if pressure fails. Proper installation is critical. An air gap must be at least twice the diameter of the supply pipe and no less than 1 inch. Reduced pressure devices and double check valve assemblies need adequate space for testing and maintenance, protection from freezing, and should generally be installed horizontally. Pressure vacuum breakers must be installed at least 12 inches above the highest fixture. Finally, these devices must be tested regularly. For a pressure vacuum breaker, the testing procedure involves notifying the authority, inspecting the valve, blowing down the test cocks, and using a sight tube to ensure the air inlet valve opens at the correct pressure. Certified testers must follow strict protocols to ensure these devices are functioning perfectly. To wrap up, cross-connection control is vital for public health. It requires shared responsibility, adherence to strict regulations, the installation of proper backflow prevention devices, and regular testing by certified professionals. By understanding and applying these principles, we keep our drinking water safe.